Okay, folks, we're going to look at this simple method of joints problem. This is probably the most simple methods of joints problem that you could actually do. A Warren truss bridge normally has equilateral triangles in it, and this is probably the world's simplest Warren truss bridge. It's got one triangle. But the reason why I'm doing it this way is just to show you a very, very simple solution to a method of joints problem. Because quite often with the method of joints problem, there's so many joints that it can become a bit overwhelming. So the first thing you need to do with a method of joints problem is solve for the reactions at the supports. And the reactions at the supports, of course, are this pin end here and this roller end. And so we are going to calculate those reactions at the supports. And there's a 5-step process for that calculation of the reaction at the supports. And the first step in that process is always to draw a free body diagram. So I will do that now very, very quickly. So we have our Warren truss. We have a point A and a point C. We know that we have 80 kilonewtons acting down at this point here. Now, up here it's acting inside the triangle, but with transmissibility of force, it's anywhere along that line. So we can put it on the outside of the body, outside of the triangle. We know that if we draw a line coming straight down here, because this is an equilateral triangle, that will intersect at the halfway point. So we know that this is 10 meters. So to this halfway point, we're going to have 5 meters. So we're doing that so we can calculate our moments and whatnot. We're going to have a reaction at A, and the reaction at A could be vertical or horizontal because it's the pin end. But because we have no forces that are horizontal, we know all the forces are going to be vertical for this particular solution, so it's a lot easier. And then we have a reaction at C as well, which is at a roller is always going to be vertical. So we now have all the information in our free body diagram. Now step 2 would be resolving our forces that are non-vertical or non-horizontal, which in this particular case we don't have any forces like that. And on the module page before this simple method of joints problem, we actually have some exercises on resolving forces that are non-vertical. So if you have a force that's acting at an angle like that, that is a non-vertical force. But we can see in this problem that all our forces are straight up and down. So we can get rid of that step completely. So step 3 is to take moments about the pin end A. So this is where we start our actual working out, and we can go clockwise is positive, so we designate our positive direction. Sigma, which is the sum of moments about the point A, is equal to 0, because the whole truss is in equilibrium, so our sum of moments is going to always be equal to 0. So we say on our next line of working out, 0 is equal to 80 times 5. Now where did I get 80 times 5? We have 80 kilonewtons acting down at the top of the triangle, and it's going to rotate the whole thing in a clockwise direction, which is why it's positive, and we have a distance from A of 5 meters. So that's why we've got 80 times 5 in this equation, and then we say minus RC, which is the reaction at C, times 10. Now why did we say minus? Because this force at C is going to push our triangle anti-clockwise, and anti-clockwise is negative. So now we just solve for C. So we end up with RC is equal to 40 kilonewtons acting up. So we know that RC equals 40 kilonewtons, so we can put that into our equation. So now step 5 is find the resultant of forces horizontal and vertical at the pin end, and we don't need to do that. We will calculate our reaction at A as well, So once we've done that, step 4, if we're doing this type of problem, is sum of verticals and horizontal forces. And we know that they're all equal to 0. So first we'll do our vertical forces up is equal to positive. Sum of forces vertical equals 0. Therefore 0 equals RAV, which is this one here that we don't know, plus RCV minus 80 kilonewtons. And we're saying minus because down is minus. So we end up with 0 equals RAV, the reaction at A, because this is a vertical force, plus 40 kilonewtons. Now, where did I get 40 kilonewtons? RC is equal to 40 kilonewtons. That's why we write that there. Minus 80 kilonewtons. And then we're just going to solve for RAV. Okay? So we end up with RA vertical is equal to 40 kilonewtons going straight up. So now we can write here that that's 40 kilonewtons. So we've already solved our reactions at the supports. So step 5 would be to find the resultant forces horizontal or vertical at this pin end here at A. But we know because there's no horizontal forces that we've already solved that. So we don't need to do that because we don't have any horizontal forces acting at pin A because all our forces are up and down. So we can get rid of our step 5. So we've calculated our forces at our reactive forces at our supports. That's our first step. Okay, so we can actually say in this box here, so we know, because step 1 was asking us to find these reactions. So we can say, if we were in an exam situation, we would say reactions, which was our first part of our question. RA equals 40 kilonewtons going straight up, and RC on the roller end is equal to 40 kilonewtons straight up. Notice that they're both the same because we have a force acting at the center of this